So now we're starting in on the third part of 451, which is gas detectors. And gas detector starts in Chapter 5 with the ionization chambers, and these are the simplest type of gas detector. Incident radiation is measured by depositing energy within a gas. This energy ionizes the gas molecules, and the resulting electron-ion pairs are collected through the application of an electric field and counted. Number 2. Average current or voltage bursts are measured in the detector but are typically small since there is no amplification of the charge. So let's start talking about that charge or that current that we're going to try and measure here. We know, we've already seen this equation and you're going to see it many more times, that voltage is equal to the charge that's deposited divided by C, the capacitance. If we were measuring the voltage, this is how we would measure it. We could also say that this is equal to I, the current, times R, the resistance. Now that capacitance is the detector capacitance, and so we write that as the dielectric constant times the area of the electrodes divided by the distance between those electrodes. Another thing that we talked about is how that charge actually moves through the gas, and that is called the drift velocity, which is going to be little v, and little v equals some quantity mu times the amplitude of the electric field divided by P, the gas pressure. Mu is the mobility. It's how easily can the electric field get the charge carrier moving. And it is a function of mass. So that is Chapter 5. Here now we start in Chapter 6 on proportional counters, and you remember the main difference of the proportional counter was that it was operating at a higher electric field where we could get enough acceleration for the electrons that they could then go create more electron-ion pairs in an avalanching event. So number 1, proportional counters rely on making the electric field large enough to create avalanches, but small enough that the pulse amplitude is still proportional to the energy deposited in the gas. That last bit, small enough, when that's no longer true, that's when we actually get into Chapter 7 with Geiger counters. Number 2, their resolution is based not only on variation in the number of charge carriers created when energy is deposited, but also in the amount of avalanching. So let's hit a couple of key equations for Chapter 6. First, we need to understand something about the acceleration of the electrons. So our acceleration vector is going to equal the charge times the electric field divided by the mass. Okay, so because it is a strong function of the mass, this is why we can accelerate electrons and not ions into avalanching. Also, we had a new detector geometry that we started looking at. We had the cylindrical geometry where my cathode radius is B, my anode radius in here is going to be little a, and we would measure our electric field at some position R is V, which is the applied bias, divided by R times the natural log of B over A. That's how we solve for the electric field within a cylindrical geometry. And lastly, we described avalanching through the Townsend equation. And the Townsend equation is my number of charges is equal to some constant alpha, which is the Townsend coefficient times n. And alpha is a function of radius, which therefore implies that alpha is a function of electric field. That's all of Chapter 6. Lastly, for gas detectors, we have the Geiger-Müller detectors, or GM detectors, GM tubes, etc. And the good news is that the equations here are all the same equations as for Chapters 5 and 6. We're just operating at a much higher electric field. So let's just quickly review the two key concepts. First, GM tubes operate at very high electric fields so that one avalanche can trigger another as a self-propagating chain reaction. Number 2, the Geiger discharge is a self-terminating process which occurs once the same number of avalanches have been reached. So all pulses from a GM tube are the same amplitude regardless of the energy deposited. I strongly recommend for studying that you actually just review this process, review what the electric field looks like and how it changes as the avalanching gets larger and larger.